So the last thing that I want to cover with concavity and points of inflection is an applied example, how this actually fits into a real-life setting. So let's read the example first and let me talk you through it. An efficiency study of the morning shift at a factory indicates that an average worker who starts at 8 a.m. will have produced Q of T equals negative T to the third plus 9T squared plus 12T units T hours later. At what time during the morning is the worker performing most efficiently? So what we want to do here is we want to maximize the rate of the worker. And now be very careful about what I just said, because that's going to be the key to figure out how we want to do this. So we want to maximize the rate of the worker. And that's going to tell us when the worker is performing the most efficiently. Okay, now when we want to maximize any equation, we know that we need to take the derivative of it. So if I wanted to maximize this equation, I would derive it. I would take the derivative of it. And that makes sense to most students. But I don't want to maximize this equation. I want to maximize the rate equation. So what we need to do then is we need to figure out what the rate equation is. So the rate equation is the derivative. So I need to take the derivative of this equation here. Negative 3t squared plus 18t plus 12. Now I have my rate equation, but now I want to maximize it. Well, if I ever want to maximize any equation, then I have to take the derivative of it. So you always take the next derivative to figure out what you want to maximize or minimize the previous equation. So now I need to take the next derivative to maximize it. So to maximize this, I need to take the second derivative, which is negative 6t plus 18. Now I set this equal to 0, and whatever that gives me is my possible critical value for my rate equation. So if I set this equal to 0, that gives me that t is equal to 3. So that is my critical value for the rate equation. Okay, now I have a critical value, but I don't know if my critical value is the maximum or the minimum or even if it's a plateau at this point. So we need to set this critical value on a number line. Now typically you think your number line goes forever in both directions, but we need to think about this in terms of my domain. So this is the only other time that domain applies when we're not talking about fractions or square roots. Domain does apply in word problems. What actually applies in this word problem? Well, if we're talking about the morning shift that starts at 8 a.m., then we know that t is equal to 0 at 8 a.m. So I know that my number line actually needs to start at 0. So I can eliminate this here on the left. It does not apply. But I'm only talking about the morning shift. So we assume that morning stops at noon. So when you're talking about 12 o'clock, then that's 4 hours later. So then your t is equal to 4. So my number line stops at 4 then because I'm only talking about my morning shift. So this part of the number line does not apply. So the only critical value that fits on this here then is my 3 value. So I need to make sure that 3 is in fact a maximum. So I do some test values in between. Now let me factor this here. If I were to take a negative 6 out, that leaves me with t minus 3. So that's going to make it a little easier to plug my test points in. If I plug in a test point of 1 or 2, that gives me my negative 6 times a negative value, which gives me a positive value, which tells me that my rate equation is increasing between 0 and 3. If I were to plug in something between 3 and 4, like 3.5, my negative 6 still stays negative, but positive 3.5 minus 3 gives me a positive, so this is negative or decreasing. So that confirms that 3 is a maximum value. So my question is then answered. At what time during the morning is my worker performing most efficiently? Meaning, when is my rate equation maximized? What's maximized at my 3 value here? So when t is equal to 3, that tells me 3 hours past 8 o'clock. So that means at 11 a.m. my worker is performing the most efficiently. Okay, let me switch this around on you a little bit then. Let me ask you a little bit of a different question. Instead of saying when he is performing the most efficiently, let me ask you when he is performing the least efficiently. Now, it might seem like a trick question because I have my number line up here and I don't have a minimum on my number line in between my 2 domain values. Well, that doesn't mean that he's just not ever performing least efficiently. That means we have to think outside the box a little bit. I'm not looking for a specific minimum value, but where I do have minimums, which is the least of the 2. So notice that my graph is going down forever on the very left-hand side of the graph, stopping at 0, or it's going down forever on the very right-hand side of the graph, stopping at 4. So if I want to figure out least efficiently, it's got to happen at 0 or at 4. This is the only time it can happen. So we need to plug 0 and 4 into our equation that we're trying to minimize, which happens to be my rate equation, to see which of the 2 is the less value. So if I plug 0 into q prime of t, that gives me out 12. If I plug 4 into q prime of t, that gives me out 36. And since this is the rate equation, this is something per something. So what this is units per hour. So at q prime of 0, at the beginning of the shift, he's producing 12 units per hour. At the end of the shift, at noon, he's producing 36 units per hour. So if we want to figure out when he's working the least efficiently, then that's going to happen at the beginning of the shift when he starts at 12 units per hour. So at 8 a.m. is when he is the least efficient. So if there's no critical value that fits into your domain, then you have to look at the endpoints to figure out which one of those 2 satisfies your condition. And so now I have just given you an example of where the second derivative is actually applicable in a real-life situation.